Well, hello, all of you. I deeply thank the organizer for the invitation. It's a real pleasure to deliver this concluding talk, even if I would have preferred to do it in person, like all of you, as I can imagine. Well, and now I am in full screen. Is it all right? Okay. Well, as you have seen on the program, my topic will be about the so-called tidal disruption events. Let me go back to begin 40 years in the past. After my 1979 paper, where I calculated the appearance of a black hole accretion disk and predicted that in the far future, the supermassive black hole at the center of M87 galaxy could be the first observational target. Well, as I believed that this could not happen within my lifetime, I immediately looked at other astrophysical processes taking place near the event horizon of massive black holes and offer indirect observational signature of their existence in the centers of galaxies. So a massive black hole with a gravitational radius, RG, provides an effective sink for stars approaching close to it. The characteristic distances involved are the following. First, you have the accretion radius here, which is the distance below which the dynamics of the stars is dominated by the gravitational field of the black hole. Next, you have the collision radius, which is the distance below which collisions between two stars are disruptive. In fact, when their relative collision velocities are higher than the escape velocity from their surfaces. A little bit closer from the black hole, you have the ablation radius, also called the Eddington radius, which is the distance below which the body receives from the central source, for example, the accretion disk of the black hole, more radiative power than its own Eddington luminosity, and consequently will start to evaporate. And finally, you have the tidal radius below which the star will be broken by the differential tidal forces generated by the black hole. Well, because the gravitational radius of the black hole grows linearly with the mass, while the tidal radius only grows as m power 1/3, well, above a critical mass called the Hill's limit here, well, the star will be swallowed by the event horizon prior to tidal disruption, making such events uninteresting from an electromagnetic point of view, although gravitational wave signals can still be emitted. And for solar type stars, the Hill's limit, as you can see here in this formula, is about 10 to the 8 solar masses. Well, now, a short historical reminder on tidal disruption begins with the work of the French mathematician Edouard Roche at the University of Montpellier in the south of France. He studied, in fact, the equilibrium figure of incompressible homogeneous body in a static field, namely in a circular orbit around a planet, and he derived the celebrated Roche limit, below which no equilibrium is possible. In fact, he wanted to explain the structure of Saturn's ring, in particular the Cassini division. Now, for the purpose of the Event Horizon Telescope and black holes, a decisive step was done in 1975 by Jack Hills here, who, like Roche, was a specialist of the solar system, but in the context of active galactic nuclei, he proposed that the gaseous fuel necessary to feed a supermassive black hole in an active galactic nucleus could be provided by the tidal disruption of stars as soon as the black hole mass does not exceed well, the typical limit of about 10 to the 8 solar masses for ordinary star, as I said previously, which is the Hill's limit. But in fact, Hills did not perform any calculation about the tidal disruption process itself. And this was the purpose of a full series of pioneering articles published between 1982 and 1989 with Brandon Carter and other collaborators, such as my student Jean Lamarck, Bernard Pichon, or Mathieu Brassard. In fact, we used the so-called affine star model with the simplified assumption that in the first stage of disruption, the star can be thought of as made of nested ellipsoidal shells. So it keeps an ellipsoidal shape. Then we were able to perform both analytical and then numerical calculation of the evolution of compressible bodies in dynamical tidal fields aimed to describe star black hole encounters along parabolic orbits. In fact, we can easily recover the expression for the tidal radius from a very simple consideration. Well, since the tidal force is a differential gravitational force, it varies like power minus 3, thus growing very quickly when the distance to the gravitational source decreases. Then you can compare just the time scale of variation of the tidal field given by this expression and the internal dynamical timescale of the star, given by this very well-known formula, and which is typically a few hundred seconds for solar densities. So you can say that far from the source, T tidal is much greater than T star. So the star can adjust progressively its equilibrium configuration to the varying external tidal field. But closer to the source, T tidal becomes quickly much smaller than T star, and the star cannot respond anymore. It undergoes a growing instability, leading to disruption. And precisely, the limiting case occurs when the two timescales are comparable, namely at the characteristic tidal radius, which is given in order of magnitude by the usual expression. When in our first paper published in 1982 in Nature with Brandon Carter, we introduced the so-called penetration factor, beta, which is in fact the ratio between the tidal radius here and the pericenter distance of the stellar orbit, the distance of closest approach, on which in fact the strength of the disruption event will strongly depend. And in fact, from simple geometrical consideration, we predicted that for large enough beta, the star could be crushed into a short-lived pancake configuration during which explosive thermonuclear reaction could be triggered. Well, in the following articles, we performed a numerical calculation based on the affine star model. So we confirmed that for moderate penetration factor, like this one, the star would be initially distorted into a cigar-like configuration, as you can see here, with the time evolution of the principal axis of the ellipsoidal star. Okay, but for deeper penetration, due to the fixed compressive tendency of the tidal tensor along the direction orthogonal to the orbital plane, well, the star will be squeezed into a pancake configuration before bouncing and exploding. You can better see the process with this pedagogical graphics from one of my semi-popular books, on black holes. So in our various papers, we showed that the maximum compression and heating in the center of the star reached during the pancake phase were strongly dependent on the penetration factor with, for instance, this exponent for a star with a polytropic index 5/3. Just for beta about 10, you get 10 to the 6 gram per cc for the central density, 10 to the 9 for the temperature during a short time scale of about 0.1 second. And these are the conditions expected for an explosive stellar disruption, producing a kind of what we call the tidally induced supernova. Well, now real black holes are, of course, highly relativistic objects, and the simple Newtonian picture that I presented until now, in fact, is complicated by general relativistic effect. And with Mark and later with Brassard, we showed that for highly relativistic orbits around a charged black hole, like this one, for instance, we get multiple compression and bounces here with this characteristic maximum temperature and time scales able to provide a new kind, in fact, of gamma rebirth as we proposed, and as apparently it has been detected a few years later. Well, now this important synthetic diagram shows the parameter space for tidal disruption. Only a star within a given triangle can be tidally disrupted by a black hole of a given mass. Here you have the mass of the black hole, and here the penetration factor. Alors here, the yellow triangle is calculated for a solar type star. So below the triangle, well, the penetration factor beta is smaller than 1, and so tidal encounters are not disruptive. Now in the upper left of the diagram here, deeply plunging orbits around small black hole lead in fact to engulfment of the black hole by the stars, because the stars are much bigger than the size of the black holes. Now, on the contrary, in the upper left, in the upper right, sorry, of the diagram, the stars encounter a black hole past the Hill's limit, and so they are swallowed whole. So a tidal disruption occurs inside the black hole and can give any electromagnetic signal. Now the interesting part, so is the inside the triangle. Here I put some dashed horizontal lines which show in fact the penetration factor which are required to achieve maximum central temperature of 10 to the 8 or 10 to the 9 degrees respectively. So you can see that, for instance, for the galactic black hole, Sagittarius A star, with his well-known mass of about 4 million solar masses, we can marginally achieve penetration factors here of about 15 and a maximum temperature of 10 to the 9. Well, but of course, the parameter space depends on the type of the star undergoing the tidal disruption. So for red giants of 1 solar masses and 10 solar radius, for instance, you have a larger triangle here in red, allowing for tidal disruption by supermassive black holes expected in some active galactic nuclei. Whereas for typical white dwarfs, the triangle is restricted to smaller black holes of intermediate mass, 10 to the 3, maximum 10 to the 4 solar masses, such as those expected in large globular clusters and dwarf elliptical galaxies. Well, of course, our initial calculation, which was based on the simplified star model, had to be checked by fully hydrodynamical calculation. And from the 90s, this has been done by a lot of excellent groups using various methods, such as the smooth particle hydrodynamics or the mesh codes. So here you have seen a movie from the excellent team of Guillaume et al., corresponding to a large penetration factor, which qualitatively confirms the squeezing of the star predicted by the affine star model. Well, now at this stage, you could rightly object that prompt tidal disruption can only produce high energy luminous flares on time scales smaller than a few seconds, and consequently that they present no interest at all for submillimeter radio astronomy, which is the subject of this conference. However, the full tidal disruption process, in fact, takes place on much longer time scales and produces many different electromagnetic signatures in various wavelengths, as suggested by this artist's view. So after the tidal squeezing phase that can be correctly described by a fan star model, the star bounces and releases its gas. So the fallback of a fraction of the stellar debris onto the supermassive black hole will create a transient accretion disk, which in turn will power luminous flares. Still later, the unbound stellar gas can interact with the interstellar medium to produce shocks. Reprocessing also from stellar matter and the interstellar medium will produce emission lines and well, a lot of observable phenomena in the aftermath of the tidal disruption itself. In fact, prior to any numerical calculation, the fact that the accretion of stellar debris should produce luminous flares had been predicted by Litsky and Ozernoid in 1979 and developed later in a celebrated paper by Martin Rees. So various numerical simulation of the aftermath of stellar disruption suggested that about half of the stellar gas will remain bound to the black hole to feed a transient accretion disk, while the other half will be ejected in the interstellar medium in the form of tidal jets, as you can see here, with expected velocity up to several thousands kilometers per second. Well, unfortunately, the post-disruption hydrodynamics is a very complicated process and is not yet fully understood. Now, from the observational point of view, the first strong candidate tidal disruption flares were found by X-ray instruments in the mid-1990s. And in the nearly 30 years since then, well, several dozens more events have been found, including in the UV and optical bands. And they are generally modelized as coming from the fallback stage of the gas onto the black hole. Well, we had also hard X-ray flares, which has been detected by the SWIFT satellite and interpreted as collimated jets from relativistic TD jets. And just added this morning, also reported a detection of neutrino from a tidal disruption event was reported at the ice cube experiment in the Antarctic. So this is paper of the day. Well, if you want to learn much more on the subject of tidal disruption, all aspects, the best reviews on all the aspects has been given by Nick Stone, in particular in his excellent doctoral dissertation of 2013, presented here at Harvard University. Well, now in my last slides, I'll try to enter a little bit more in the scope of submillimeter radio astronomy, although it is not at all my field of competence, as you know. Well, indeed, a few TDE candidates have been detected in radio and interpreted as gas outflows. The first detection, as far as I know, was associated with a transient Swift J1644, involving a supermassive black hole of 10 to the 6 or 10 to the 7 solar masses at a distance of about 50 megaparsecs. So the total radius of such a black hole is between 5 and 50 astronomical units, whereas at this distance, the spatial resolution of the Event Horizon Telescope is only 10,000 astronomical units. But anyway, radio observation have been performed in VLBI and several instruments. And you can see here briefly some radio light curves observed over a period of about 200 days. A more recent interesting detection was ASASN 14 Li, which is associated with a galaxy at 90 megaparsecs here. And well, this small diagram coming from paper by the teams of Alexander, Berger, and others shows, in fact, the radioluminosity of a few tidal disruption events as a function of time here, extending up to 600 days. So this provides, it's clear that radio observations provides the opportunity to follow the tidal disruption events on a rather long period of time. Well, from the earliest TDE candidates, it was really clear that multi-wavelength observations are key for distinguishing TDU from other sources of high energy emission. So a crucial factor in this story is the estimated rate of tidal disruption events. Various modelizations agree on an average rate between 10 to the minus 4 and 10 to the minus 5 event per year and per galaxy. But with observational surveys up to a redshift of 0.8, for instance, well, this gives as much as 10 to the 4 events per year. And as I said before, upcoming sky surveys will find in the next future TDU in the hundreds or thousands, including in the X-ray bands with LOFT, in the optical band with the large synoptic telescope survey, and also in the radio with SCA, which has opened recently, as you know, and hoping the next generation Event Horizon telescope. Now, to be still closer to the targets of the next generation Event Horizon telescope, I'll finish by briefly discussing the special cases of Sagittarius A star and M87 star. So for the galactic black hole candidate, until recently, the most tightly bound star known was SO2 here, which orbits with a period of 16 years with a pericenter distance of about 120 astronomical units. So I recall that the tidal radius of the galactic black hole for a solar type star is only 1 astronomical unit. This corresponds to, and in fact, the angular size of the tidal region is about 200 micro arc seconds, so well in the scope of the resolution of the Event Horizon telescope. Much recently, the much dimmer star, SO102, has been discovered to lie on an 11-point-year orbit. And last month, the Gravity collaboration in Chile made measurement of the new star, S62, a very faint star, which could have a much closer pericenter distance, up to 5 astronomical units. But in all cases, all these stars remain far from the tidal radius, and none of them is doomed to be destroyed by the tidal field of the galactic black hole. And in addition, the tidal disruption rate for a solar type star is estimated for galactic center to be only 10 to the minus 5 per year. So it's clear that the hope of observing directly such an event in the galactic center is extremely low. Well, but why not think about the tidal disruption of bodies much more numerous than stars, namely asteroids? Well, first, on the observational side, short flares are currently observed in the near infrared at a frequency of about 1 event per day, as clearly shown by the teams of Genzel and Ghez, got the last Nobel Prize in physics for this kind of observations. Well, second, it has been reported by several authors that sub-millimeter flares are observed about 1 hour later, the previous ones, within a distance of 1 astronomical unit, which is precisely the size of the tidal radius for bodies with density about the solar density, namely a few grams per cc. Well, third, we can reasonably assume that the galactic black hole is surrounded by a kind of super Oort cloud of asteroids containing up to 10 to the 14 asteroids larger than about 10 kilometers. Now, since asteroids have the same average densities as solar type stars, they have the same tidal radius, namely 1 astronomical unit for the galactic black hole. And the disruption of incompressible body, such as planets and asteroids, in contrast with compressible body for stars, in a dynamical tidal field was calculated also in one of our seminal papers of 1986 and later by other researchers like Kostik and Calvani. And in fact, we find 2 regimes of disruption depending on the penetration factor, namely a cigar-like disruption in most of the cases, and a disk-like disruption here in the strongest encounters. So by the way, well, it's more or less a joke, but why not? This could explain the shape of the mysterious object Oumuamua that crossed our solar system in 2017, as you know, if Oumuamua is interpreted as a piece of a tidally disrupted extrasolar asteroid rather than an extraterrestrial spaceship, as claimed by one of your prestigious colleagues. So now Zubovas et al. Have proposed the following interesting scenario. With a total of 10 to the 14 asteroids in the super Oort cloud, the tidal disruption rate could be around 300 events per year. So contrarily to highly compressible stars, in fact, broken asteroids would be broken into smaller pieces. And well within the Eddington radius, the ablation radius, the fragment would be vaporized by the radiation of the accretion disk around the black hole, producing multi-wavelength flare extending to the sub-millimeter band. And so we could have an explanation of the flare, sub-millimeter flare, observed in the galactic center. And it's an interesting possible explanation involving tidal disruption, not of stars, of course, but of asteroids. And to conclude, what can be said about M87 and supermassive black hole, which are in quasars and blazars, and which are the more massive targets for the Event Horizon Telescope? So as I said before, we cannot, of course, expect tidal disruption outside the event horizon of black hole above the Hill's limit. But stars can be destroyed by high velocity star-star collision. So for instance, around a 10 to the 9 solar masses black hole, the typical collisional velocities exceed 5,000 kilometers per second within a distance of 0.1 parsecs from the black hole, which is a rather large volume. And these collisions are highly disruptive. So as Carter and myself, we pointed out in our letter to Nature of 1982, there is a very interesting analogy between the collisional disruption of a couple of stars here and the tidal disruption of a single star which in some sense can be considered as a collision of the star with itself, because in both cases, the strengths of the event can be characterized by what we call the crushing factor. So in the case of tidal disruption, it is the penetration factor. In the case of collision, it is a ratio between the collisional velocity and the escape velocity. And so the same value of the crushing factor should produce the same kind of phenomena. For instance, short-lived pancake configuration for crushing factors, about 10, followed by a violent ejection of gas, streams, relativistic jets, and so on. So in fact, supermassive black hole could also be interesting candidate to show some effect, not coming from tidal disruption events, but from collision disruption events observable in the radio band. But, well, in fact, unfortunately, contrarily to tidal disruption, the collisional breakup of stars at high velocity has been poorly studied with hydrodynamical simulation. But I really believe that this is a very promising subject of investigation for the next decades, both from theoretical point of view and observational point of view, including the extension of the next generation event horizon telescope network very far, maybe up to the moon. Although I probably will know, I will no longer be there to see the results. All right, it's finished. Thank you very much for your attention.